Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight we're going to learn about Johannes Kepler. So as you make yourselves comfortable, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Tonight, we're going to talk about a man who changed everything. A man who looked up at the night sky and refused to accept the answers everyone else was perfectly happy with. A man who was born premature, half-blind, and into a family that made the Kardashians look functional, yet somehow managed to unlock the secrets of planetary motion that had eluded humanity for thousands of years. His name was Johannes Kepler, and he is, without question, one of the most fascinating people who ever lived. Not just because of what he discovered, but because of how he discovered it, and who he was while doing it. This isn't going to be a dry recitation of dates and laws. We're going to dive deep into the messy, beautiful, tragic, and ultimately triumphant life of a man who truly believed that God was a mathematician, and that the universe was a grand cosmic symphony waiting to be understood. We'll talk about his obsessions, his failures, his mother's trial for witchcraft, yes, really, and how he revolutionized our understanding of the cosmos while barely scraping by financially. So, settle in, and I promise you, by the end of this lesson, you'll understand why this neurotic, nearsighted German genius deserves to be remembered as one of the greatest scientific minds in human history. Chapter 1. A distinctly unpromising beginning. Johannes Kepler was born on December 27, 1571, in the town of Weil-der-Stadt in the Holy Roman Empire, which was, as Voltaire famously quipped, neither holy nor Roman, nor an empire. It was basically a patchwork of German-speaking territories held together by political duct tape and religious tension. And speaking of tension, let's talk about the Kepler family, because, wow, if you think your family reunions are awkward, be grateful you weren't born into this clan. Kepler's father, Heinrich, was a mercenary, a soldier for hire who fought for whoever would pay him. He was violent, unreliable, and frequently absent. When Johannes was 5 years old, dear old dad nearly got executed for various crimes. He disappeared when Johannes was 17 and was never heard from again. Father of the year, everybody. His mother, Katharina, was no picnic either. She was quarrelsome, had a terrible temper, and this is important for later, was widely suspected of being a witch. She raised herbs, brewed strange concoctions, and had a personality that made people nervous. In an era when being an unpleasant woman could literally get you burned at the stake, Katharina was playing with fire. Metaphorically, and, as we'll see, almost literally. Johannes himself was born 2 months premature. He was a sickly child, small, frail, and plagued with health problems his entire life. He nearly died from smallpox when he was 4, which left his hands crippled and his eyesight permanently damaged. For a man who would spend his life studying the heavens, having terrible vision is a bit like being a food critic with no sense of taste. It's not ideal. Despite all this, the poverty, the dysfunction, the physical ailments, young Johannes showed signs of brilliance early on. He was intellectually curious, mathematically gifted, and deeply religious. The Lutheran Church recognized his talents and sponsored his education, which was essentially his only ticket out of a life of poverty and misery. He attended the University of Tübingen, where he studied theology with the intention of becoming a Lutheran minister. But fate, or providence, or sheer cosmic irony, had other plans. While at Tübingen, Kepler studied under Michael Maestlin, one of the few astronomers who secretly accepted the Copernican model of the solar system, the radical idea that the Earth orbited the Sun, rather than the other way around. This was dangerous territory. The Copernican model contradicted both common sense and church teaching. It suggested that humanity wasn't at the center of the universe, which was theologically troubling and philosophically unsettling. But to Kepler, it was beautiful. It was elegant. It was, he believed, the truth. In 1594, before completing his theological studies, Kepler was offered a position teaching mathematics in Graz, Austria. He didn't particularly want to go, he wanted to be a minister, but the Lutheran Church insisted, and Kepler, ever dutiful, accepted. This was the pivot point. This was when Johannes Kepler, who should have been a small-town preacher, became instead a revolutionary astronomer. And it all started with a geometry lesson that gave him what he believed was a divine revelation. Chapter 2. The Cosmic Mystery and the Platonic Solids. Picture this. It's July 19th, 1595. Kepler is in Graz, teaching a geometry class probably to students who couldn't care less, when suddenly, mid-lecture, he has what he later described as a divine inspiration. He's drawing geometric figures on the board, and he notices something. If you inscribe a triangle inside a circle, and then inscribe another circle inside that triangle, and keep alternating circles and polygons, you get ratios. Specific ratios. And Kepler thinks, what if this is how God designed the solar system? Now, let's pause here. This is important. Kepler wasn't just a mathematician or an astronomer, he was a mystic. He believed that God had constructed the universe according to mathematical principles, and that by understanding those principles, he could glimpse the mind of God. This wasn't just science to him, it was worship. So Kepler gets obsessed with this idea. There were 6 known planets at the time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. 6 planets, 5 intervals between them. And do you know what else there are 5 of? The Platonic solids. The 5 perfect 3-dimensional geometric shapes. The tetrahedron, 4 sides. The cube, 6 sides. The octahedron, 8 sides. The dodecahedron, 12 sides. And the icosahedron, 20 sides. Kepler's idea was this. What if the spacing between the planetary orbits was determined by these 5 perfect solids nested inside each other? What if you could fit the orbit of Saturn around a cube, and the orbit of Jupiter inside that cube, and then fit that inside a tetrahedron, and so on, all the way down to Mercury? It's a beautiful idea. It's elegant. It's geometrically satisfying. There's just one problem. It's completely wrong. But Kepler didn't know that yet. He spent months calculating, measuring, adjusting, trying to make the model work. And sort of did kind of if you squinted and were generous with the data. The fit wasn't perfect, but it was close enough that Kepler convinced himself he'd discovered the hidden architecture of the cosmos. In 1596, he published his findings in a book called Mysterium Cosmographicum, The Cosmic Mystery. It's a wild book full of elaborate geometric diagrams and passionate arguments about the divine structure of the universe. It's also, from a modern perspective, mostly nonsense. But here's the thing, it wasn't completely nonsense. Buried in all the mystical geometry was something genuinely revolutionary. Kepler was the first person to insist that there must be a physical cause for planetary motion. He argued that some force emanating from the sun pushed the planets around in their orbits. This was a radical break from the traditional view, which held that planets moved because it was simply their nature to move, or because angels pushed them. Kepler was groping toward the idea of gravity more than 80 years before Newton would formalize it. He didn't get there, he thought the force was somehow magnetic, but the instinct was right. Physical causes, mathematical laws. This was the beginning of modern physics. The book made Kepler's reputation. He sent copies to all the major astronomers of Europe, including a cranky, brilliant Danish nobleman named Tycho Brahe. And Tycho, despite thinking Kepler's geometric model was ridiculous, was impressed enough by the young man's mathematical ability to invite him to come work as his assistant. This was either the best opportunity of Kepler's life or the worst. Possibly both. Chapter 3. Tycho Brahe, or how Kepler acquired the best data in the world while being driven slowly insane. Let's talk about Tycho Brahe, because you cannot understand Kepler's life without understanding Tycho, and Tycho was a piece of work. Born in 1546 into Danish nobility, Tycho was brilliant, eccentric, and almost comically arrogant. As a young man, he got into a duel over a mathematical disagreement and had part of his nose cut off. For the rest of his life, he wore a prosthetic nose, reportedly made of brass and copper, glued to his face, sometimes gold and silver on special occasions. Imagine that, a man walking around Renaissance Europe with a metal nose. Tycho built the finest astronomical observatory in the world on an island given to him by the King of Denmark. For 20 years, he made astonishingly precise observations of the stars and planets, the best observations anyone had ever made. But Tycho had a problem. He was a brilliant observer, but he wasn't a great mathematician. He collected data obsessively but didn't know what to do with it. Enter Johannes Kepler. In 1598, religious tensions in Graz forced Kepler, a Lutheran, to flee Catholic-controlled Austria. He needed a job. Tycho needed someone who could make sense of his mountains of data. It seemed like a perfect match. It was not a perfect match. Tycho was paranoid, controlling, and secretive. He wouldn't let Kepler see most of his data. He gave him small, specific problems to work on, always keeping the big picture to himself. He treated Kepler less like a colleague and more like a useful tool. Kepler, meanwhile, was brilliant, neurotic, and completely dependent on Tycho financially. He was also painfully aware that Tycho had the data he needed to unlock the secrets of planetary motion. So, despite being frustrated, insulted, and occasionally humiliated, Kepler stayed. The two men worked together in Prague for less than 2 years. Tycho would dole out little bits of observational data. Kepler would perform calculations and beg for more access. They argued constantly. At one point, Kepler actually quit and left, only to return a few weeks later because he had nowhere else to go. And then, in October 1601, Tycho Brahe died suddenly after a banquet. The exact cause is unclear, maybe a bladder infection, maybe mercury poisoning, maybe he just ate and drank himself to death. There's a persistent legend that he died because he refused to leave the dinner table to urinate, which would be the most aristocratic way to die imaginable. The autopsy remains disputed to this day. But here's what's not disputed. Tycho died, and Kepler, within days, was appointed imperial mathematician in his place. And more importantly, Kepler now had access to all of Tycho's data, decades of precise observations, particularly of the planet Mars. This was the opportunity Kepler had been waiting for. He later wrote that if he hadn't obtained Tycho's observations, he would never have been able to discover his laws of planetary motion. Tycho's data was that good, but getting the data was only the beginning. Now Kepler had to figure out what it meant, and that process would take him 7 more years, drive him to the brink of madness, and force him to abandon some of his most cherished beliefs. Chapter 4. The War with Mars. Kepler called it his War with Mars, and it's one of the most dramatic stories in the history of science. Here's the situation. Kepler had Tycho's observations. He knew where Mars appeared in the sky at hundreds of different dates, measured with unprecedented precision. His job was to figure out the shape of Mars's orbit to create a mathematical model that would predict exactly where Mars would be at any given time. This should have been straightforward. For 2,000 years, everyone knew that planets moved in circles. Circles were perfect, and the heavens were perfect, so obviously planets moved in perfect circles. If the observations didn't quite fit, you just added more circles, little circles rotating on big circles, called epicycles. It was complicated, but it worked, sort of. Kepler was a Copernican, so he believed the planets orbited the sun, not the Earth. But he still assumed the orbits were circular. He spent months calculating, adjusting, trying to find the perfect circle that would match Tycho's observations of Mars. He couldn't do it. No matter how he adjusted the parameters, there was always a tiny discrepancy about 8 arc minutes or 8/60ths of a degree. That might not sound like much, but Kepler knew Tycho's observations were accurate to within 2 arc minutes. If the model disagreed with Tycho's data by 8 arc minutes, the model was wrong. Most astronomers would have fudged the numbers. 8 arc minutes? Close enough. But Kepler couldn't do it. He wrote, "Out of these 8 minutes, we will construct a new theory that will explain the motions of all the planets." Think about that. 8 arc minutes, a measurement so small you could barely see it with the naked eye, and Kepler was willing to throw out 2,000 years of astronomical tradition because of it. So he started over, and over, and over. He tried different types of circles. He tried moving the sun slightly off-center. He tried different speeds. Nothing worked. He later estimated he did the same calculations 70 different times, trying to make circles work. And finally, after years of failure, Kepler did something radical. He abandoned circles entirely. What if, he thought, the orbit wasn't circular at all? What if it was an oval? He didn't know what kind of oval, not yet, but he started calculating what an oval orbit would look like. This was insanely difficult. Remember, Kepler didn't have computers. He didn't even have calculators. He was doing all of this by hand, pages and pages of tedious arithmetic, multiplication, division, calculating distances and angles and speeds. His manuscripts are filled with calculations. It's exhausting just to look at. But slowly, painstakingly, Kepler began to see patterns. He discovered that if Mars's orbit was an ellipse, a specific type of oval with 2 focal points instead of 1 center, and if you put the sun at one of those focal points, then the observations matched perfectly. An ellipse, not a circle. The heavens weren't perfect after all. Planets didn't glide along in stately, uniform circles. They swung in and out, speeding up when they were closer to the sun and slowing down when they were farther away. And then Kepler discovered something even more beautiful. He noticed that as Mars moved along its elliptical orbit, it swept out equal areas in equal times. In other words, if you drew a line from the Sun to Mars and watched it sweep across the orbit, the area covered in, say, 30 days in January would be exactly the same as the area covered in 30 days in July, even though Mars would have traveled different distances. This is Kepler's second law. A planet sweeps out equal areas in equal times. It's called the law of equal areas, or sometimes the area law, and it's deeply strange. It means planets don't move at constant speeds. They speed up near the sun and slow down far from the sunday. But there's a hidden regularity, a mathematical harmony underneath the apparent irregularity. And here's what's extraordinary. Kepler discovered this law before he discovered the first law. He found the pattern in the speeds before he found the shape of the orbits. Only later did he realize that the orbits were ellipses. So the famous 3 laws of Kepler aren't actually in the order he discovered them. They're organized logically, not chronologically. Kepler's first law: planets orbit the sun in ellipses with the sun at one focus. Kepler's second law: a planet sweeps out equal areas in equal times. In 1609, Kepler published these findings in a book called Astronomia Nova, The New Astronomy. It's one of the most important books in the history of science. It's also one of the most difficult to read, because Kepler didn't just present his conclusions. He walked the reader through every failed attempt, every wrong turn, every calculation. It's like a detective novel where the detective shows you all the wrong suspects before revealing the killer. But that's exactly why it's so important. Kepler showed that science isn't about instant revelation. It's about grinding, difficult, painstaking work. It's about being wrong dozens of times and having the courage to start over. It's about following the evidence even when it contradicts everything you believed. Kepler's war with Mars had been won, but he still had one more law to discover. And it would take him another 10 years to find it. Chapter 5: Music, Mathematics, and the Harmony of the World. While Kepler was doing all this astronomical work, his personal life was falling apart. His first wife, Barbara, whom he married in 1597, died in 1611. She had never been particularly happy with him. She found him tedious and overly obsessed with his work, which, fair enough, he was. Two of their children had already died young. Kepler was devastated, grief-stricken, and suddenly alone with two surviving children to raise. The Holy Roman Empire was also descending into chaos. The Protestant Reformation and Catholic Counter-Reformation were tearing Europe apart. Religious violence was everywhere. The 30 Years' War, one of the most destructive conflicts in European history, would soon begin. Kepler, a Lutheran working for a Catholic emperor, was constantly caught in the middle. And yet, somehow, in the midst of all this chaos, Kepler kept working. He couldn't not work. Astronomy wasn't just his job, it was his calling, his purpose, his way of understanding God's creation. In 1612, he published another book, De Nive Sexangula, on the six-cornered snowflake. It's a short, charming meditation on why snowflakes have six-fold symmetry. Kepler didn't have the tools to answer the question. You need modern chemistry and crystallography for that, but he asked it, which was the important thing. It's considered one of the founding documents of crystallography. The same year, Kepler remarried. His second wife, Susanna, was reportedly much better suited to him, patient, kind, and willing to tolerate his eccentricities. They went on to have 7 children, though not all survived to adulthood. Child mortality rates in the 17th century were appalling. Through all of this, Kepler kept searching for patterns. He was convinced that the universe was harmonious, that there were hidden mathematical relationships connecting everything, and in 1618, he found another one, Kepler's third law. The square of a planet's orbital period is proportional to the cube of its average distance from the Sunday. Let me say that again, without the mathematical jargon. If you take the time it takes for a planet to complete one orbit, its year, and multiply that number by itself, and then you take the planet's average distance from the Sun and multiply that number by itself 3 times, you get 2 numbers that are always in the same proportion for every planet. For example, Earth takes 1 year to orbit the Sun, and its average distance from the Sun is 1 astronomical unit, by definition. 1 squared is 1. 1 cubed is 1. The ratio is 1 to 1. Mars takes 1.88 Earth years to orbit, and its average distance is 1.52 astronomical units. 1.88 squared is 3.53. 1.52 cubed is 3.51, basically the same number accounting for rounding. This works for every planet. Mercury, Venus, Jupiter, Saturn, all of them follow this same relationship. It's a mathematical harmony binding the entire solar system together. Kepler was ecstatic. He had found it, the deep hidden order he'd always believed was there. He published it in 1619 in a massive, sprawling book called Harmonices Mundi, the harmony of the world. And when I say massive and sprawling, I mean it. The book is divided into 5 parts, covering geometry, architecture, music theory, astrology, and astronomy. Kepler genuinely believed these were all connected different aspects of the same divine mathematical plan. He calculated the music each planet would make based on its speed. Faster planets have higher pitches, and suggested that the solar system was literally a cosmic symphony, with each planet contributing its own voice. Modern scientists tend to politely ignore the music of the sphere's stuff and focus on the third law, which is genuinely profound. It was the final piece of the puzzle, the mathematical relationship that connected all the orbits into a single unified system. These 3 laws, elliptical orbits, equal areas in equal times, and the period-distance relationship, completely revolutionized astronomy. They destroyed the ancient notion of perfect circular motions. They showed that the universe operated according to precise mathematical laws, not philosophical principles or divine whim. And critically, they set the stage for Isaac Newton. 50 years later, Newton would use Kepler's laws to derive his law of universal gravitation. Kepler had described how planets moved. Newton would explain why. But Kepler would never know that. He had his own problems to deal with, because while he was discovering the laws of planetary motion, his mother was on trial for witchcraft. Chapter 6. The Witch of Leonberg. In 1615, when Kepler was 43 years old and at the height of his scientific career, his mother, Katharina, was accused of witchcraft. This wasn't a minor accusation. This was deadly serious. The witch hunts were in full swing in Germany, and people were being tortured and executed with disturbing regularity. The charges against Katharina were detailed and specific. Neighbors claimed she had made them sick with her potions. One woman said Katharina had poisoned her with a mysterious drink. There were allegations of consorting with the devil, of cursing people, of causing livestock to die. Was any of it true? Almost certainly not. Katharina was elderly, unpleasant, and quarrelsome. She collected herbs and mixed remedies, which made people suspicious. She had also made the mistake of suing a neighbor over a petty dispute, and that neighbor's family decided to retaliate by accusing her of witchcraft. In an era when being an unpopular old woman was essentially a death sentence, Katharina was in terrible danger. Kepler dropped everything. He was imperial mathematician, one of the most famous scientists in Europe, and he threw all his prestige and energy into defending his mother. He wrote legal briefs. He hired lawyers. He traveled back and forth between Prague and his hometown of Leonberg, desperately trying to navigate the legal system. The trial dragged on for 6 years. 6 years of accusations, interrogations, and legal maneuvering. At one point, Katharina was imprisoned in chains. The prosecutors wanted to torture her, standard procedure in witch trials, to extract a confession. Kepler managed to prevent that, but just barely. Finally, in 1621, after Katharina was brought before the instruments of torture and shown exactly what would happen to her if she confessed, and she still refused to confess, the court reluctantly acquitted her. She was released, but the experience had broken her. She died 6 months later. Kepler was traumatized. He wrote bitterly about the ignorance and superstition of the people, about how his mother had been persecuted for no reason except that she was difficult and unpopular. But he had saved her life, which is more than most children of accused witches could say. The whole ordeal also probably inspired one of Kepler's strangest works, Somnium the Dream. It's a science fiction story, possibly the first real science fiction story ever written, about a man who travels to the moon and describes what the Earth would look like from there. It's filled with scientific speculations about astronomy and physics, but it's also full of weird mystical elements, including a protagonist whose mother is a witch who summons demons. Kepler wrote it partly as a thought experiment. How would astronomy look from another world? But also, perhaps, as a way of processing his mother's trial. The book wasn't published until after his death, but it influenced later writers and is now considered a landmark in the history of science fiction. Chapter 7. Decline and Death. The 1620s were not kind to Johannes Kepler. The 30 Years' War was devastating Central Europe. Protestant and Catholic armies marched back and forth, burning cities, slaughtering civilians, spreading disease. The Holy Roman Empire was disintegrating. Kepler's patron, the Emperor Rudolf II, had been forced to abdicate years earlier. His successors were less interested in astronomy and less willing to pay Kepler's salary. Kepler was constantly broke. He spent much of his time writing letters, begging for back pay, traveling from city to city trying to collect debts. He published a final major work in 1627, the Rudolphine Tables, an enormous set of astronomical tables based on Tycho's observations and Kepler's laws. It was a massive achievement, but it didn't make him rich. He also kept trying to get his geometric model from Mysterium Cosmographicum to work. Even after discovering that orbits were ellipses, not circles, he still believed that God had designed the solar system using the Platonic solids. He spent years trying to fit elliptical orbits into his geometric framework. It never quite worked, but he never gave up on it either. This is one of the fascinating contradictions of Kepler. He was capable of extraordinary, clear-eyed rationalism, willing to abandon 2,000 years of astronomical tradition because the data didn't fit. But he was also deeply mystical, convinced that the universe was a divine puzzle that could be solved through geometry and numerology. These two sides of his personality existed simultaneously, and both were essential to his genius. In 1630, Kepler left Prague for the last time. He was tired, sick, and desperate for money. He traveled to Regensburg to try to collect some of the salary he was owed. He arrived in Regensburg in November 1630. Within a few days, he developed a fever. He grew delirious. On November 15th, 1630, at the age of 58, Johannes Kepler died. He was buried in Regensburg, but his grave was destroyed during the 30 Years' War. No trace of it remains. Chapter 8. Legacy. So what do we make of Johannes Kepler? Let's start with the science. Kepler's 3 laws of planetary motion are fundamental to astronomy and physics. They work. They're not approximations or models that work pretty well. They are precise mathematical descriptions of how planets actually move. We still use them today. When NASA sends a probe to Mars, they use Kepler's laws to calculate the trajectory. When astronomers discover exoplanets orbiting distant stars, they use Kepler's laws to characterize the orbits. The Kepler Space Telescope, launched in 2009, discovered thousands of planets beyond our solar system, using techniques directly descended from Kepler's work. His laws also paved the way for Newton's theory of gravity, which in turn paved the way for Einstein's theory of relativity. You can draw a direct line from Kepler's calculations to modern cosmology, but Kepler's importance goes beyond the specific laws he discovered. He fundamentally changed how we do science. Before Kepler, astronomy was largely about saving the appearances, creating mathematical models that predicted where things would appear in the sky, without worrying too much about whether the models reflected physical reality. Kepler insisted that the models had to be physically real. There had to be actual causes, forces, mechanisms, real things happening in space. He also insisted on precision. 8 arc minutes mattered. Small discrepancies couldn't be ignored. The universe didn't run on approximations. It ran on exact mathematical laws, and the job of the scientist was to find those laws, no matter how difficult. This was revolutionary. This was the birth of modern science. As we understand it, the idea that nature operates according to mathematical laws that can be discovered through careful observation and calculation. And he did all of this while struggling with poverty, religious persecution, family tragedies, and a body that never quite worked right. He was half-blind, frequently sick, and emotionally fragile. He suffered from what we would probably now diagnose as depression and anxiety. Yet he persevered. He kept calculating, kept thinking, kept searching for patterns. He genuinely believed that by understanding the cosmos, he was understanding God. His science was his religion. His calculations were his prayers. There's a famous passage in Harmonices Mundi where Kepler, after discovering the 3rd law, writes with barely contained joy, "I thank you, Lord God, our Creator, that you have allowed me to see the beauty in your work of creation." This wasn't false modesty or pious window dressing. Kepler really felt this way. To him, there was no contradiction between science and faith, between mathematics and mysticism. The universe was God's masterpiece, and mathematics was the language in which it was written. Modern scientists tend to separate these things. We talk about Kepler, the scientist, rigorous, empirical, mathematical, and politely ignore Kepler, the mystic, with his music of the spheres and his Platonic solids and his astrological speculations. But you can't really separate them. The mysticism and the mathematics were part of the same project. Kepler discovered the laws of planetary motion because he believed those laws existed and were discoverable. He was willing to do years of tedious calculations because he was convinced there was a hidden harmony waiting to be found. In a way, Kepler represents a bridge between two worlds. He was the last of the great mystical astronomers, the ones who believed the heavens held secret meanings and divine messages. But he was also the first of the modern astronomers, the ones who insisted on mathematical precision and physical reality. He lived at exactly the right moment in history to be both. A generation earlier, and he wouldn't have had Tycho's data or the Copernican model to work with. A generation later, and the mystical approach would have been completely out of fashion. But in Kepler's time, you could be both a mystic and a scientist, and nobody thought it was strange. Well, some people thought it was strange. Kepler was considered weird even by the standards of his time. But weird in a productive way. Weird in a way that changed everything. Chapter 9. What Kepler can teach us. So here we are, more than 400 years after Kepler's death, and we're still talking about him, still using his laws, still inspired by his story. What can we learn from this neurotic, half-blind, obsessive genius? First, that greatness often comes from unexpected places. Kepler was born into poverty, raised in dysfunction, physically weak, and personally awkward. He had every reason to fail. But he had intellectual curiosity, mathematical talent, and an iron will. That was enough. Second, that real breakthroughs require courage. It takes courage to throw out 2,000 years of tradition because of an 8 arc-minute discrepancy. It takes courage to say, everyone before me was wrong, and here's why. Kepler had that courage. He trusted the data more than he trusted authority. Third, that failure is part of the process. Kepler failed constantly. His geometric model from Mysterium Cosmographicum was wrong. His first attempts to model Mars's orbit were wrong. He probably tried and discarded 100 different ideas before finding the ones that worked. But he kept going. He didn't treat failure as a reason to quit. He treated it as information. Fourth, that precision matters. 8 arc minutes. That's all it took to overturn the entire astronomical worldview. Kepler could have ignored that discrepancy. He could have said, close enough. But he didn't. He insisted on getting it right, and that insistence changed everything. And finally, that you can be brilliant and still be human. Kepler was not a perfect person. He was difficult, neurotic, sometimes petty. He made mistakes. He clung to ideas that were obviously wrong. He wasted years on calculations that went nowhere. But he also loved his children, grieved his losses, fought for his mother, marveled at snowflakes, and believed deeply in the beauty of the cosmos. He was fully, messily, complicatedly human. And somehow, this flawed, struggling human being managed to peer into the heavens and understand them in a way nobody had before. He found order in chaos. He found harmony in what seemed like randomness. He found the music in the spheres. That's the real miracle of Johannes Kepler. Not that he was superhuman, but that he was so very human, and yet achieved something transcendent anyway. Epilogue. Looking up. I want to leave you with one final thought. On clear nights, when you look up at the sky, you're seeing what Kepler saw. The same stars. The same planets. Mars, still following its elliptical orbit, still sweeping out equal areas in equal times, still obeying the laws that Kepler discovered 400 years ago. But here's what's different. We understand what we're seeing. We know the planets aren't gods or wandering spirits, or points of light affixed to crystal spheres. We know they're worlds actual, physical worlds moving through space according to mathematical laws. And we know this largely because of Johannes Kepler, because he looked at those same lights in the sky and refused to accept easy answers, because he calculated and recalculated until he found the truth, because he believed that the universe made sense, and he was determined to prove it. The planets are still dancing. They've always been dancing. But Kepler taught us the steps. That's his legacy. That's his gift to us. So the next time you look up at the night sky and you see Mars glowing red against the darkness, remember Johannes Kepler. Remember the half-blind mathematician who fought a war with Mars and won. Remember that science isn't about knowing everything. It's about being willing to question everything. It's about following the evidence wherever it leads, even when it contradicts what you believed yesterday. And remember that greatness isn't reserved for the healthy, the wealthy, or the well-connected. It's available to anyone willing to look carefully, think clearly, and work tirelessly toward the truth. Johannes Kepler was born premature and sickly into a dysfunctional family in a backwater town in the Holy Roman Empire. He should have been nobody. He should have been forgotten, but he wasn't. Because he looked up at the sky and asked questions, and he didn't stop asking until he found answers. That's the power of curiosity. That's the power of persistence. That's the power of believing that the universe can be understood, if only we're willing to do the work. Kepler did the work, and we are still benefiting from it today. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.